is the case for transmit-only communication. So some of the students are very well versed with this topic, but I thought some of the other people at WINLAB probably only have a peripheral view, so hopefully this will give them a better view of what the research is going on in this group. Okay, so and just to say that I'm presenting, but there's a lot of people who have been involved with this effort for a long time. Okay, so as you've probably seen some of these slides before. So there's this idea that there's an opportunity because of Moore's law, right? So Moore's law says this is the year on the x-axis, and this is the number of transistors per chip on the y-axis. And the yellow line here is for the x86 family, so this is 2005, 2010 here. The red line here is the transistors in a memory, in a DRAM. And then the purple line here is the projection from 1975, assuming doubling every 18 months. Okay, and you can see that Moore's law has been true for a long time, since at least the early 70s. It's been following this linear scale on a log, or linear curves on a log scale. So this is a log scale on the x-axis. Okay, and then Gordon Bell came up with this idea of Bell's law, which is just that every 10 years, because of this constant shrink, you get a new computing class. Okay, so originally there were mainframes and then mini computers. People here are probably too young to remember those. And when I was a kid, there were mini computers. When I was a kid, there were mini computers. And then there were workstations and PCs and laptops and PDAs and cell phones. And now here's our GPIP tag here. Okay, so the platform keeps getting smaller and smaller. And part of the vision is, and this isn't a real platform, is could you get it down to something that fits on your finger? And the same technologies used, the same CMOS technologies used for radios and sensors and processors. So that's the opportunity, right? The opportunity is we've got these much smaller platforms, what can we do with them? So everyone said, oh, this is great, we have these small platforms, we could use them for all these new and interesting application domains where we need small platforms with sensing and communication. So things like emergency response, healthcare, you could have body networks because you have these very small computers on you. Outdoor applications. So this was Intel sponsored a application where they were sensing in a vineyard. And the idea is if you knew the temperature, humidity, and light, then you could try to figure out when the right time to pick the grapes was. And this is for Rich Howard. You can see the size of the battery. This is the battery, and this is the sensor node. And this was just for one season, so like 4 months. But you could also have like fire detection or other environmental monitoring. You could have home and office applications. That's what we do a lot of here. Logistic applications. Okay, so this vision's been around for a while. You can see here this is a very old PDA. This is a Palm. So people were talking about. I ripped off this slide from 10 years ago. So it's a Palm Top. Okay. And so one of the things that, if you look at the literature from 10 years ago or 15 years ago, people kept talking about sensor networks. And so the idea here is that we have a collection of these small devices. They have some kind of wireless communication. They form some kind of ad hoc network. And they use this ad hoc network. So these are supposed to be these wireless nodes with sensing. These are supposed to be communication links. And then eventually they route around obstacles and send the data to the outside world. Okay. And you saw a lot of research on things like how to do multi-hop communication, how to do ad hoc networking, how to do aggregation and compression, because the sensor nodes typically aren't very big, not very powerful, and they don't have a lot of energy. Energy conservation, because again, a lot of times the nodes are mobile. And lots of novel operating systems and programming languages. So this was kind of the overview of sensor networks. And you see this idea keep cropping up in different contexts. So to be a little cynical, my dad's you have a research area, it lives for a while, and then it doesn't pan out, so then you give it a new name and you reapply for funding with this new name. So we had smart dust, sensor networks, Internet of Things. Internet of Things is pretty old, it's from 2004. It's getting recycled. Ambient intelligence is formed, so these were all kind of very similar ideas. But 15 years later, we haven't really realized this widespread deployment of these kind of networks yet, right? So anybody wearing body sensor networks? Anybody have like a smart home? I have one sensor in my home, so I have the one sensor smart home. Okay, but right, it hasn't really reached the scale where people thought it would. And it's been quite a while, so what happened? Okay, so the problems that people thought were very important, some of them are still important, but energy conservation, scaling sensors, efficiency of code and data size for small sensors, and routing in these ad hoc networks. So people thought these were very important problems, and they worked a lot of research on those. But what I would argue is we sort of hit kind of a technology barrier in a sense. And one of the barriers is that, and I'll talk a lot about this in a couple slides, which is, so a lot of the academics tend to ignore this idea of, you know, how much does it cost to deliver one of these networks versus the value that people get out of it. So I'd argue that the sensors themselves are still too expensive for most applications. Okay? And even though it's easy to publish research papers on novel operating systems and programming languages, there's like a backlash, which is it's actually very difficult to develop applications in these novel environments. Okay? So it's a big minus. And that the other thing that happened was people would develop like stovepipe solutions, so they'd have one kind of sensor and one kind of mesh network for a given application, but it was too hard to reuse that same infrastructure for lots of different applications. And the result wasn't general purpose. So, you know, again, that gets at, you know, it's too expensive for lots of applications. What you like is one infrastructure for many applications, so you can amortize that cost over many applications. So just like your laptop, you know, it can run games, it can run a word processor, right? It can run a Lisp application. Okay, we can't reuse that same infrastructure for many different applications. People didn't think about it in a general purpose way. Okay, so one of the big themes about this talk, and this is what I hope to get across to students, is that sometimes less is better. So at a system level. So what transmit only really is, I would argue, is an example of less is better. And what less is better means is one level of the system kind of performs one task, and you move functions that you need to other layers of the system. Okay, and the result is an overall system improvement. And we can see this in many other system areas. Okay, so I just picked 3 examples here. So in computer architecture, there was RISC versus CISC. So RISC is reduced instruction set computing, and CISC is complex instruction set computing. And the idea here is that if we reduce the instruction set and make the resulting instructions run faster, okay, and punt a lot of the optimization and abstraction to the compiler and language, you get an overall system improvement. Okay, and that was definitely true. And you have to remember that CISC at the time was really countering the VAX instruction set architecture, and VAX really is CISC. Okay, so x86 is weird, but it's not CISC. I mean, VAX, no, it's true. x86 is weird, it's not orthogonal. So you can't use every register for anything you want. Right, but it's not like it has multiplied polynomial in the instruction set. So VAX, you can actually call an instruction that takes 2 vectors and will do polynomial multiplication on 2 vectors. Okay, at the instruction set level, which is kind of ridiculous, but at the time, well, no, at the time, right, they were trying to raise the abstraction level to the programmer because a lot of people program in assembly language. Okay, but that was the wrong thing to do. It was better to leave that to the compiling language. Okay, IP versus ISDN and ATM. Okay, so IP is really just focused on, so you're networking people, right? It's really just focused on packet switching. So all the quality of service, all the call switching, call state, and all that other stuff, you punt to the edges. You make the endpoints perform those functions, and the core router is just routing IP packets. That's it. Okay, and so that architecture, so it makes the switching, you know, scale better and simpler and cheaper. Okay, at the expense of maybe making the edges a little bit more complicated. Okay, but that turned out to be the right trade-off. Because it took, you know, ISDN was proposed, and for a long time it was hard to make it work, and there were no products on the market. Okay, and ATM suffered a similar kind of fate. It took a long time to get any ATM switches on the market. When they did come out, they were very complicated and very expensive and slower compared to IP switches. Okay, at the time. So I remember I had to work on ATM switches. I was like, this thing's so slow. So it turned out that that was the right trade-off. And for operating systems, so I don't know, I guess, you know, at Berkeley they make everyone read the Multics paper, which is incredibly painful, but it's good for the soul. Okay, so Unix was a reaction against Multics. Okay, what was Multics trying to do? Multics was trying to do a lot of things. But the thing I think that really killed them was this idea of object persistence in the operating system. Okay, so most people know object-oriented programming here, right? Like you have C++ or Java. Right? So imagine you created an object, but that object stayed persistent in the operating system, and then any program that ever ran could reference that object and use it. Okay, so that's what they were trying to do. Right? So I knew an object, and then the operating system would automatically save it to disk and allow dynamic linking for any application to use that object. And that's actually a really hard problem to solve correctly, and it made the system like very complicated and slow. And so then when the Dennis Ritchie and the Bell Labs guys have rejected that model and a much simpler model called So this is all examples of where less is better. Okay, so transmit only is an example of less is better. Okay, so the first key insight that we need is that when you're dealing with sensor data, most of it is in this class for communication, and since this is WINLAB, you guys should be aware of this. A lot of applications are in this class where you can tolerate actually losing some data and never getting it back. Okay, so applications in this class are like, you can think of like audio and video. Okay. Another one that somebody pointed out, I think was Ben, was video games. Okay, so in a video game protocol, right, a lot of times they're broadcasting state about where the players are or what's happening. And if you lose a packet, you just wait for the next state update and you throw away the past. Okay, so typically these are in a pattern where like the past isn't really that important if you have present state. So audio and video are similar, right? If I'm listening to something right now, I don't really care that maybe I lost something in the past, right? I want to see the thing right now. So kind of like the past is the past. Okay, but these kind of protocols are not really suitable for things like documents. Right, so it's not like, oh, if I lost like some bits in my Word document at the front, then that's okay. Like that's not okay. So the kind of protocols we're talking about are these probabilistic reception protocols where losing some data for real isn't the end of the world. Usually you care about the most current data. Okay? So that's the kind of communication we're talking about.
The historical data can still be like a cache or stored.
Right, I mean it's still useful, but if you lose it, it's not like I have to get it back for my application to work. Okay, so that's a very important distinction, because this isn't going to work if that's true. So if it's true that I really have to have the nth byte, and I can't make forward progress until I get it, then this doesn't work.
Yeah, my point is, even at the transmitter only, those historical data still can be available in the network.
Yeah, no, it's what I mean by probabilistic is we're likely to get all the data, but some data won't. So, right, so here in this model then, sensors only transmit and sense with a specified periodicity. So that makes all the sensors one hop, because that's all they do. Okay, and we add a small amount of randomization to keep things from colliding all the time forever. Okay, and what we do is, which is different from a mesh network, is we have a small set of receivers that cooperate to reconstruct the sense data. Okay, so instead of a mesh network where all the nodes are equivalent, we have this asymmetric design where we have sensors only sense and transmit, and then we use a network of cooperating receivers to reconstruct the sense data. And this network obviously has to have, the network connecting the receivers has to be much more powerful than potentially the sense network. Okay. So the backhaul bandwidth has to be higher than the sense bandwidth. And we have some initial results that show what factors you need for this. It's not ridiculously high, but it's still, factors of 4 and 5 higher. And so we threw out a lot of stuff. Okay, so maybe this should go on another slide. We threw out a lot of stuff. So what did we remove? Well, we really removed everything we could possibly remove. Well, not everything, but we've removed a lot of things, and we can still remove some more things. So remove things like sensing the channel before transmission. Okay, you don't need that anymore. Throw it out. So that's CSMA. Carrier sense. Right? Should get rid of it. Acknowledgements. So request to send, clear to send. Throw that out. Precise clocks and synchronization. Okay, so to do time division multiple access, you actually need some kind of synchronization, right? If everyone gets a timing slot to send their data, then you need some kind of synchronization, and you need a good clock. Okay, so throw that. Because actually, clocks are power hogs. Okay, good clocks are. And signal feedback. So if you look at like a MIMO kind of style protocol with multiple antennas, they have this kind of round trip feedback loop in order to get the MIMO to work. And we don't know any of signal feedback, just throw it out. So it's really only transmit. So we got rid of a bunch of stuff.
So one quick question.
Yeah.
So I know you're focusing more on the communication part here,
yeah.
But if energy is one of the things, then what about storage? Is that something that you throw away as well, or
yes.
Is that an outcome?
Very little storage, almost no storage. Okay. So the basic model is you sense, you just transmit. Now you could sense and buffer some of them and then transmit, but we haven't even done that. We just sense and transmit. So we have very, very little storage.
Right, but how does storage, keeping storage on, affect energy, versus the communication
That's a good question. Storage to a point can be helpful. So there's a trade-off between the likelihood of, if your packets are very long, they're likely to collide. So there's some point where buffering everything and sending it in one huge packet isn't helpful. On the other hand, there's a trade-off between, I guess, the energy you need for storage and the energy you need for transmission. And actually, I'm not so sure the energy you need for flash writes. Actually, haven't done that calculation. I don't know. I'm going to look at Rich. Is turning on the flash more expensive than sending over the air?
I think a better question is that if you store it, that implies that you're going to use it later.
Well, no, you could buffer a whole bunch and then try to amortize the...
But that doesn't matter, because remember, it's the channel fill factor is the only thing that determines...
Yeah, well, you're amortizing some of the preamble and stuff over data.
Yeah, I mean, that's...
But even if you are, you're still not having huge amounts of storage, right? You're talking a few factors, so 5, 6 packets.
So does the storage
it's not a lot of storage.
consume energy better?
Sure.
Oh yeah, no, to turn on flash
Why
runs.
have CD squared F? You have to turn the flash on and run it with a clock.
Yep.
But I think Ben has a good point, which is, how would you actually
You
use
need
it
to,
later on? Right.
like, refresh it
So that's
every...
actually has to die in.
How
Flash
much
is
is
good to
energy?
flash, but to write takes energy.
To write the flash
To write,
is not
okay.
free.
But the store there doesn't...
Oh, no,
really-
no energy once it's stored, but you have,
Okay.
you have to pay to write it and pay to read it, so it's,
Yeah.
Mhm.
it's just
And the
not
write-
time dependent.
The write is
Okay.
not free as far as I mean, that's something we should look at.
Yeah.
Because it's not clear to me that writing to flash versus sending over the air, they may be roughly equivalent. Flash writes, because it has to change
It should
the
be
cell.
smaller, right? Writing the flash then...
Not clear.
Should be smaller than...
No,
Sending
no.
the air.
No, not clear.
Not there.
Right, because if you look at a flash write, first of all, there's this big setup time,
Mhm.
right? So the time you're setting up and waiting for the flash chip is, you're not doing anything. So you're just burning energy from not doing anything.
Okay.
Right? So now writing to RAM definitely is cheaper, right? But that's volatile. So.
Oh, flash RAM. But RAM should have some power to keep it, right?
Right. So you could have low power sleep RAM again. I don't know
Uh-huh.
what that trade-off is. So. Or if your application can get its power out. Okay, so getting back at this, but those are good questions. Storage and stuff. So focus on getting sense data. Then we threw a whole bunch of stuff. This really saves energy on the sensor. And the other thing is, probably people here realize this, but not everybody does, which is that receiving data has a similar energy cost. It's about the same to receive a bit as transmit a bit. Okay, so every bit I receive over the air is costing me as much energy as transmitting the sensor bit. Okay, so all the like for example, in RTS-CTS protocol, okay, every bit that I'm spending transmitting RTS-CTS packets is not data, so that's overhead, and it's costing me the same energy as actually transmitting the data. Okay, and this is because the way radios are built, and I think there's something fundamental here about sending communication waves, but we haven't figured it out yet, is that amplification just costs a lot of energy, and so when you have amplifiers, you're just burning a lot of energy. Okay, so the other thing it does, though, in addition to saving all this power over the air, is it really simplifies the sensors, because now you're doing a lot less. So because you're doing a lot less, you don't need as much stuff on the sensor. You don't need, there's fewer components. You can buy cheaper components, and we'll see real data on this in a couple slides. And the sensors are physically smaller. Okay, so that enables more applications. Okay, and it also simplifies the programming model to the next level up in the stack, because now, you don't have all this like aggregation and compression and trying to figure out like what the data really was, uncompress it and all that stuff. It's just, every time unit I get some sense data. So even if we buffer with storage, we similar programming model. So it's very similar, or a simple programming model that, it's easier to build higher layers on top of that. All right, so what are the challenges? Well, some are semantic. So, what applications can really tolerate some loss? So if it's only 1 in 1,000 or 1 in 10,000 or 1 in a million. Right, as I mentioned before, I don't want 1 in 10,000 bytes of my Word document to be lost. Maybe that's okay. But yeah, some applications can't tolerate loss. And does the wireless channel utilization really any good with transmit only? So there's an old theoretical result on unslotted aloha that says the maximum channel efficiency you can get with unslotted aloha, which is basically the protocol we're proposing, is limited at 18%. And this is true with the assumptions they make, but we'll show why some of those assumptions aren't true and how we can get better than 18% channel efficiency. And then this receiver network, if we're using this network of receivers that are tightly connected, then is the complexity of this receiver network too high? Is it not worth that trade-off? Is the energy use of this too high? How many of these do we need, and how connected they have to be? Okay, we'll show we have real results for these. This receiver network is not, for most applications, an undue burden for the benefits we get back from transmit. And then manageability and security. Manageability is something we've been thinking about, which is how do you change the parameters on the sensor? If it's really only transmit only, then you can't change anything on it. So is that okay for a lot of applications? Or if you do want to change something, how do you do it? Okay, so we've been thinking about that. And then security, how do you perform lightweight unidirectional security? Still, I would argue, a problem. And this we've thought even less about. So I'll have a few sketchy ideas at the end of the talk, but we haven't thought about that at all. Okay, so what's the outline for the rest of the talk? I'm going to talk about the improvements we get by simplifying the sensors. I'm going to talk about how we can recover the channel efficiency by exploring the capture effect. How we can build applications from this simplified programming model, and a few sample applications that we have actually built. Okay, so sensor simplicity. Okay, so academics tend to ignore this, but I argue this is actually pretty important if the technology is actually going to ever get realized, which is how much does it actually cost to put sensors on stuff? Okay? So some applications are enabled if the sensor cost is like $100. That's kind of like traditional Berkeley mode. $10 enables more applications. $1 would enable a lot more applications. And people even talk about 10 cents and 1 cent. So even 1 cent would enable lots of applications. So if your sensor is really 1 cent, like some of the RFID people keep claiming, you have 1 cent sensors, then you could label every product ever made. So not every product ever made, but almost every product could be labeled with a sensor. I think 10 cents and 1 cent is not realistic. $1 and $10 potentially, or we have $10, $1 potentially. Okay, and the other thing I want to get across is that these cost assumptions, and this is actually probably more important for the other places than here, but cost assumptions based on Skilling's Moore's law, they omit real engineering design constraints that are real. Okay, and I think after 15 years, it shows that these design constraints are actually fundamental. Okay, and that we're at sort of the lower bound of cost of the sensors given these real design constraints. Okay, so I'll show you later in the talk a $10 sensor, and that was with a lot of work. And I don't think we're going to get below a couple of bucks for $5 to $10 sensors anytime soon without not just volume increases, but real changes in the sensor design. Okay. And I'll argue that transmit only actually does reduce the cost by several factors. And we have real data to show that we can drive the cost down of a Berkeley mote usually goes for about $80. And so we have sensors that are about $10. So that's a factor of 8, which is pretty good. And getting to this, how can we drive down to $1? Unless there's a true single chip sensor, which is actually quite hard to do, and I'll show why that's in the talk, we're still going to be in this order of dollars or something. Okay, we're never going to get down to $1.
So will the battery on the same Moore's law curve?
No, so batteries aren't, but the battery we're using is only 15 cents.
Yeah.
Okay,
It's a lot less than that in quantity.
What?
It's a lot less than that in quantity.
No, it's about 15 cents.
If you want to make $1 million, you'd get them for under
12.
10.
Okay, I don't know. Even at quantity 1,000, they're still like 15 cents. So maybe
That's
at quantity million, they're 10 cents.
That's strategic.
Yeah. Maybe at quantity million, they're 10 cents. But even a battery at 10 cents, right? You still have 90 cents to get to the $1.
Yeah.
So that I think
So
is
the chips
possible.
are the bigger cost than the battery. The battery is just not a problem.
Well, that's true if you can use a coin cell battery. So if you're using AA batteries, then you're at, well, no, 2 AA batteries is still only,
It's
not that. They're like 50 cents each or something. So you're still down in the dollar regime roughly. Okay, so here's two sensor boards. So what I'm going to do in the next couple slides is compare two sensor boards. So this is the Telos B. This is from 2004. This is kind of one of the. This is maybe a second generation sensor board. They haven't really changed that much since then, actually. And this is the transmit-only PIP that we developed here at WINLAB. And both have an antenna, radio, microcontroller, battery. Okay, but qualitatively, this is like a factor of 8 cheaper. So why is that? Oh, and also smaller. Okay, so here, see, this uses 2 AA batteries. The other interesting thing was the actual physical board size was built to match these AA batteries. Okay, so one of the things you see is you worry about your power constraints. You pick a battery and then you build your sensor around that battery. Okay, so this was for both these sensors. That was kind of the mentality for building the sensor. Okay, so they picked AA's and we picked a coin cell, and then built the design around that. All right, so what are these fundamental engineering costs that you just can't get around? Okay, so one of them is just component count. Okay, so when people use Moore's law scaling rules, they tend to ignore the other components that aren't ICs on a sensor and sort of abstract those away and not worry about them. But that actually really impacts the cost. And so what this is showing for various sensor designs that I can find the bill of materials for. Okay, if we just go through and count both the number of ICs, which is the blue bar, as well as the number of non-IC components, which is the red bar, okay, and compare the component counts, we see that the transmit-only design, we worked pretty hard to cut the number of components down, and it does cut the number of components down, but you still have, order roughly 20 non-IC components on the board. Okay, and a Telos B has, over 75 non-IC components on the board. So these don't scale with Moore's law. So, and these are going to add cost to the board, and so that's why you're always going to be at this dollar level or multi-dollar level. So, and then there were other designs too. Robomo was from UCLA, Epicor was from Michigan, and Mica was from Berkeley as well. So, and just to give you an example of how the technology scaled, so GPIP4 is sort of similar in functionality to Telos B. It's a little bit stripped down. But even there, the component count is still sort of order 50 components. Okay, and that was with a lot of work trying to. Okay, so just comparing two boards for the actual cost. So I went through the bill of materials, I went to DigiKey and Mouser and found the cost for all these things in quantity 1 through quantity 1,000. Okay, so what this x-axis is showing you is Telos B in quantity 1, transmit only in quantity 1. Okay, Telos B in quantity 10, transmit only in quantity 10. Okay, and if you look at just the components, so this doesn't include the cost of building the board and also assembling the board. Okay, so the cost of the assembly scales with the number of components as well. So more components is more assembly cost. And you can see here that in quantity 1, right, just to buy the parts for the moat of nothing else is almost 60 bucks. Okay, so when you're paying $80 for a moat, that's actually not that far off. And even if they build them in quantity 1,000, the parts cost is still, about $25. So, and you can see the transmit only is, this factor of 8 less. The other thing you should notice is that you do see the volume scaling rules coming out of this data. Okay. So roughly every factor of 10 in volume reduces cost by roughly 20%. Okay, remember this is going from 1 to 1,000. And you see that for both the transmit only and the Telos B one. So what about single chip solution? Okay, wouldn't that solve all our problems? So the answer is no. Well, yes and no, but I'm going to argue that there are existing single chip solutions and they don't really solve the problem. Okay. So this is a recent chip from TI that came out a year ago, the CC430F61, which is basically a CPU and a radio on the same chip. Okay, and this is the reference design. Okay, and what you should get out of this reference design is this is a single IC, but it still has 39 analog components. So even with this single IC, you still need these 39 analog components. So when we looked at using this chip versus our existing TO design, it wasn't a clear win. because you still need a lot of analog components to make this work. Okay, and the right way you can think about it is these analog components are isolating different parts of the chip from each other. Okay, so you can't like just get rid of them. It's not that easy.
They're external, right?
Right, the components have to be external, but if you're trying to isolate various parts of this chip from each other, like the radio from the CPU, you need these big capacitors and stuff. Okay, so you can't just get rid of it. And then to build a big capacitor in CMOS is not like CMOS processes like that easy. Right? So, most of these are capacitors. I think they're almost all capacitors except for there's 2 resistors and a couple of inductors for the antenna. Okay, but you still need an antenna too, right? So you're going to need this stuff. So I guess the argument here is that single chip isn't going to solve all your problems unless your CMOS design is so good that you can really get rid of all this stuff. And I'd say that's really the challenge for the CMOS designers that I'll throw out there, which is, can you really get rid of all this stuff? Okay, and until you can, then the cost is still going to be in the order of a couple bucks.
People have been trying for decades. Physics is wrong.
Physics
Chemistry
is wrong. Yeah, no, it's hard to get rid of those external components. I'm not saying it's easy, but until we do, we're still going to be in this regime where we're like $5.
But what is the ratio of the cost? This is 69 analog components should be very cheap, right?
Well,
they cost money to install, and they use up board areas, so both of those add in.
Right. It's actually not the cost of the component as much as the assembly cost. Okay, so that's what kills you.
It's done with a robot, one piece
Even the
at a
robot.
time. One piece
Right.
at a time. You pay by the second for it to do that.
Yep.
So you may want to mention Intel's recent announcement of their slightly more digital radio, right?
Yep. It's slightly more digital. It still probably has a lot of analog components,
But it scales a little bit better.
yeah. But even Intel can't get rid of all these external components.
No.
I'm saying it's a hard CMOS problem. But I guess my point is that these are real engineering barriers that are like for real, that you can't just say, oh, Moore's law is going to get rid of everything and solve all the problems. Okay. Because at some level we're already there, right? So if all the IC stuff's already on one chip, then Moore's law is done. Right, because these analog things they're not transistors part of scaling. All right. Okay, so just as a little comparison, and some of these numbers I need to re-verify. So I think a TO PIP is about 2 years lifetime. Telos B is about 3 to 4 months lifetime for roughly sensing once a second.
Also list the battery size there.
Yeah, this is 2 AA's, and this is the
So
CR32.
the Telos B is like 20
Well,
times the actual energy.
Right. So, the other thing is that the physical size is also much different. So this is about 1 inch by 1 inch by 0.2 inches versus, this includes the battery holder, like 2.2 by 1.2 by roughly 0.7 inches. Okay, and the component cost, right, TO PIP at quantity thousands 5 versus Telos B is 6. So you see that factor of 8 roughly. This is factor of 5. Telos B's on the curve a little bit more. Okay. And now getting to what about channel efficiency in the receiver network? So can we get back this channel efficiency? So remember from your undergrad networking days, hopefully you did unslotted aloha, okay, where you just transmit when a packet's ready and you don't do anything else. So that's basically transmit only. And the traditional analysis says that if you have a collection of transmitters, the maximum channel efficiency is 18%, okay, because the probability of a collision grows the number of transmitters. And is transmit only stuck at this 18%? Do we have to sacrifice this much channel efficiency compared to CSMA or TDMA, okay, which have efficiencies like you can push up to over 90%? Okay, so the answer is no. And what we're going to do is very aggressively use the capture effect. Okay, and so what's the capture effect? Well, radio uses electromagnetic waves to communicate. And so if you're in this regime of communicating using waves, then a strong wave will overpower a weaker wave. Okay, so that's the right intuition. So if you have simultaneous reception of packets with different signal powers, then if one of them is much stronger than the other one, the strong one will recover the bits from, and the weaker one looks like noise. Okay, so what this is showing is the receiver position on the x-axis and the received signal power on the y-axis. And if we had 2 transmitters, right, if we slide our receiver, there'll be some regime where we'll receive a lot of power from transmit A, we can recover all the data. or transmitter B, we can recover all the data. And then there's some region in space where they're roughly equivalent power, and we can't get the bits out from either one, if there's a collision.
So it's both like preamble capture and data capture? So actually there are two types of capture. One is the preamble capture. Another is called data capture.
Right, we don't really distinguish between preamble and data capture because for us, either capture the whole packet or you don't. So
that's data capture.
But yeah, I mean, even if we capture the preamble, it doesn't really help us if we can't get the bits out. So the two methods we use to leverage the capture effect are message and messaging. So this is the basic idea of message and messaging is you sense when the stronger signal arrives, and you only start decoding when the stronger signal starts. And then you can also do, remember I said we have this network of cooperating receivers? Okay, depending on where you physically put the receivers, okay, you'll be close to the transmitters, and then you can capture packets out. Okay, so I'm going to talk for a little bit about message and messaging and then receiver replacement. So this gets at, I hope answers your question. So we're not really looking at the difference. So we have these 5 cases here. So what this is showing is time on the x-axis, and then different scenarios for a collision on the y-axis. So in one scenario, there's no collision, so that's great. In another scenario, so the stronger packets in pink and the weaker packets in gray. So in this scenario, the data is collided with, but the preamble sync is not. Here the sync is, then here the packets totally overlap, and then here just the preamble is collided. So the question is, can we recover the pink packet no matter what case is happening? And the answer is yes. And what we do is we do, as mentioned before, so this is an example of 2 receivers that are cooperating. So you can build a very cheap message and message receiver from just combining 2 single receivers. Okay, and this is the algorithm for doing it, actually. It's quite simple. So if I see a preamble, right, I'm one of these, and I'm connected with just a few bits. So this is, I guess, power, ground, and data. Right, so if I see a packet, then I tell the other radio to start receiving. And if, when I finish recognizing a packet correctly, I also tell the other radio that I finished seeing a packet. So what this does is, if I see a preamble and tell the other radio to start, okay, it allows me to, if the second packet is stronger, then the other radio will start decoding when the second packet arrives, the stronger packet. So one of the 2 radios will get it. Okay, in this case, if a radio is in the middle of receiving a packet that's garbage, it can abort, okay, and restart. So what this says is, I recognize the packet correctly. Whatever you're receiving, just drop it because I already received it correctly, and you start receiving a new packet. Okay, so that's what this case happens. Okay, and that basically builds a message and message receiver that can handle all those 5 cases. Okay, so now let's look at some results about how well this actually works. So what this is showing is the relative signal power in dB between 2 packets, okay, a strong one and a weak one. And this is the probability of successfully decoding the packet. Okay, and these were these different cases. So in no collision, basically the probability of receiving packets is 100%. So in case 1, where the stronger packet arrives first, and then the weaker packet arrives second, as long as the difference in signal power is, roughly 4 dB, then you have like an over 90% chance of capturing the packet. And as more of the packet gets overlapped, so that's case 2 and case 3, or region 2 and region 3, you have less likely chance of receiving the packet depending on the signal power difference. But even at 6 dB, you're basically receiving pretty close to 100% of the packets from one of those 2 receivers. So take-home message is, as long as the received power is different by 6 dB, then we can handle all the first 3 cases.
So on the green line,
Yeah.
the dip, is that significant?
The green line there, the dip is, oh yeah, I didn't even notice that.
No,
Well, good
it's-
thing the person who's in the room who
No,
generated the graph.
It was just experimental error because
Okay.
I didn't really care
Yeah,
at that
that's
side.
what it seems.
Yeah, and if you look at, you notice that the
Yeah.
error bars are bigger there, and that's because they didn't collect a lot of samples there because they didn't think it was important.
So So that's experimental error because the grad student didn't think it was worth it. Right?
Well, it's not, so you see from -6
No, no,
you're getting
yeah,
the
I
whole
mean-
thing. You know, when you get the +6, you're sure you're getting the whole thing. Too.
Yeah, I mean, who knows? Maybe somebody turned on the toaster then or something. Okay. All right.
I mean, it has to do with how many samples I collect.
Yeah. All right. So let's look at those other cases that are hard. I would argue are harder. So these are where the stronger packet occurs after the weaker packet. Okay. So this is cases 4 and 5, and you see here that. What do I show here? Okay. So for case 4, that's where the preamble and sync word were both overlapping, and you see here again. This is this black curve. So once again, actually here about 4 dB, we can capture the stronger packet pretty close to 100% of the time. And then if just the preamble is overlapping, actually we have a higher chance of capturing the packet. That's the blue line. And then if only half the preamble is overlapping, and we don't actually have message and messaging, there's still some likelihood of capturing the packet, but it's only about 30%. Because this is without message and messaging. If just half the preamble overlaps. To answer your question.
So what's different between a half preamble overlapping?
Well, region 5 means the entire preamble overlapped.
Yeah.
Okay, and region 5 with half means just the first half of the preamble overlap. So even less of the packet overlapped.
But this perform like
So
worse.
why is
This,
that?
well, this is without message and messaging at all. So if you just have
Oh, okay.
receiver with no message and messaging, even if only half the preamble
Oh,
overlaps,
okay.
you still get something.
Yeah, yeah,
okay,
yeah.
but it's only about 30% chance. And then you see here that if you have half the preamble overlapping and message and messaging, that's the green line that it's close to 100%.
Ah.
So it's just showing that, right, even in this case, even a single receiver does something, but it's not great. Or, well, 30% is not.
So, but it has required like two radio.
Right, so all the message and messaging is to radio.
So the chip does not support this.
Right, you could build a chip with it, but we
Yeah.
use 2 radios that communicate.
That's just because, you know, these cheap low power chips tend not to. There have been a few Wi-Fi
Yeah.
cards that do.
Yeah.
But
Yeah, you could build it all in one chip.
Yeah, I
But-
think Wi-Fi they support
Yeah.
something. This
But-
preamble.
This is a cheap hack that actually works pretty well.
So
but-
this messaging is basically just the timing, the starting point of the second radio, right?
Yes.
It's not doing any like the data.
Nope, it's just timing the set. Yes, right.
Okay.
And
So-
this depends on the distance between the two.
well, so the two should really be seeing the same environment. It would be, you know, best if they somehow shared the same antenna if that was possible. But yeah, I mean they're in the same location, so they're seeing the same,
Almost the same.
you know, radio environment.
It should be the distance with some lambda, half lambda, or some numbers.
Well, it's okay if they're coupled, right? It's okay if the two antennas are coupled.
Oh,
So
okay.
we're not trying to get two different samples of the environment. We're not trying to do like some kind of MIMO simultaneous receiving.
Yeah.
It's just when you have one packet on top of the other packet, you just want to get the strongest packet.
So to
Because the
this
weaker one is
share-
dead no matter what. You just want to make sure you always get the strongest packet.
So is there one antenna or two antenna?
So, I mean,
Each radio has one antenna. There's 2 radios, each with one.
Just want to get the starting point of
The strongest packet. It's just timing, right? This is all just
Yeah.
timing.
because I mean, notice like the part where you have no MIM, that brown line, it's not relative to dB. You're just missing it because of timing, because you're missing too much of the preamble. So there's a chance that you just don't see the packet.
Right. Right. If your preamble, if it's set, the settings are wrong after the preamble, then you'll miss it.
Yeah.
So, you can take care of 2 packets overlapping. If there are multiple packets, then you need more ports coupled together.
You just keep flipping back and forth. So whenever
No, exactly. If there
Yeah,
were
so
multiple,
we do-
if there were 3 packets overlapping, I mean, the way that
Well, one is busy with one,
Well, so
the other one is
this
busy
is
with
this is the way you should explain it. Right? Whenever one radio sees a packet, that packet must have been strong enough to successfully receive the preamble and sync. Right? So it tells the other radio, I'm receiving a packet. If you thought you were receiving a packet, it must be garbage now because I'm receiving a packet that's enough stronger than it that I actually see it. The other radio should give up and start listening again. Right? So that you're only ever listening to it. There's only ever one strongest packet.
Right.
The
Well,
other
right.
one
The algorithm
is
is right. If
background
I
is
The other one is just noise.
yeah, if I start receiving a packet, then the other radio should turn on in case the stronger packet comes later.
Yeah.
Or if I receive a packet, just turn on later. And if I just correctly decoded all the bits, whatever they're receiving, they should stop.
And they should
and start
reset
receiving
immediately
again.
because
Yeah.
they see another
Yeah.
stuff.
Because I just received all the bits.
Okay.
Yeah, that's
So
the
it
algorithm.
can keep hopping as they can. Okay.
But if the two, if two signals are similar, and there is still a chance, like one receiver get correctly decoded the first one, right? Because it's overlapping, and it get the first part synchronized well, right? And so the second receiver
Cause an abort.
get another, like if another signal comes in, and so this board will tell the other one receive the
Once
second.
I decoded all the bits correctly, it tells the other board to stop doing whatever it's doing and start receiving again. If it's in the middle of receiving a packet, you just stop. Right? Because the other board got all the bits. So if you're in the middle of receiving another packet, you should just give up the string. Okay, so moving on to receiver placement. So this is, can we physically place the receivers close to transmitters to get most of the data? So there's this idea of a capture disk. So here we have two transmitters, okay? And what the idea of a capture disk is, if I place a receiver anywhere in the circle, this is abstraction, okay, then I'll get all the packets from transmitter 1 relative to transmitter 2. Okay, so if there's a collision between transmitter 1 and transmitter 2, a receiver anywhere in the circle will get transmitter 1's packet. Okay, so that's the idea of a capture disk. And what we're going to do is exploit this effect to place receivers. So there's this algorithm called F-Embed. So this is a very high-level view of the algorithm. So here we have 3 transmitters, okay, and we want to figure out where should we put the receivers to maximize the total amount of traffic in the channel or in this plane. Okay, so we have these 3 receivers. Each pair generates a capture disk, so that's what these circles are. Okay, and then for each capture disk, a possible placement of receivers in the center of the disk or at the intersections. Okay, so those are called solution points. Okay, and then what we can do is enumerate all the solution points. So we get a bipartite graph of solution points and transmitter pairs that are covered by those solution points. So that means that this receiver will capture all the packets from these transmitters. Okay. So this is this bipartite graph, and then we're going to search algorithm on this bipartite graph to generate the top number of receivers that capture the data. And that's the basics of F-Embed. And the problem is F-Embed on its own is order n to the 6, which is pretty slow in the number of transmitters. So Rob here, or is it you or you and a bunch of other people, came up with the approximation, which is more order n squared. Mesh, but it still works almost as well as F-Embed. So F-Embed is the exact solution. Gives you provably lower bound. This does no provable lower bound, but in practice it's almost the same. Okay, and so just
n is number of
transmitters.
How many receivers?
Yeah, how many receivers? So to decide.
So usually it doesn't scale with number of receivers that much because the number of solution points. You're right, it does scale with the number of receivers, but usually the receivers is so small. Or for the problems we're looking at, the receivers like 10 and the transmitters might be like 1,000. So this n to the 6 is totally dominated by number of transmitters for most of the real applications.
It would just be number of receivers
times number of
n to the
transmitters.
sixth.
Yeah.
Right, which isn't.
Yeah.
So you want to
Just,
like
it's just multiplying both.
Yeah, no, you could. It's really
I guess
right.
you're
N would be
Yeah, that's true.
no, right. So right. So typically, this side of the bipartite graph is way shorter than this side. Okay. But you're right that the total solution. No, actually.
No, it's by far dominated by the transmitter.
Yeah, I mean this side's way bigger than this side. So.
And the assumption is the location of the transmitters is kind of fixed.
Yeah. It's,
Yes.
It's known and fixed.
Well, right. You couldn't run if transmitters are mobile,
I
then
guess I didn't
this
really consider it
kind of
If
bipartite
we keep
approach.
going, that's really covered.
And that's not under design space sort of. So I'm not going to change the location of the transmitters to improve my probability of reception. I can only.
The way the algorithm works is very stat-wise. It says, here's the transmitters, where's the best place for the receivers. Yeah. It's not. You could imagine an algorithm in this kind of framework that the problem is if you move the transmitter, solution points move. So then you have to somehow factor in what happens when you have changing solution points, which is algorithms.
So one way to think about it is if you have probabilities of where the transmitters will be,
Yeah.
you could put out, a topology of transmitters to generate solution points for that matches that probability distribution, right?
Or something, yeah, or you could have some probabilistic graph algorithm, but we
Yeah,
didn't
but
look
the
at that.
easiest way to do it would be like if this room was, the expected value of transmitters in this room is 10,
Yeah.
then just put 10 uniform transmitters in this room. And do the same thing for every room in the lab,
Oh.
and then generate solution points, right? I mean, that's pretty
Yeah, yeah, yeah.
straightforward, because if that's how you expect the transmitter to
Yeah,
be
but-
deployed, then...
But I would say, Kash's thing is right, which is we haven't looked at making the algorithm more probabilistic.
Yeah, but I mean, that's,
Ability-
no, I have, Rich, and that's
Oh,
the
you have?
solution.
Okay.
That's the
Well, that's
solution. So
one-
if you have some expected value of
Right,
transmitters
right.
for all your
One solution
locations-
is to use expected value transmitters. I mean, if you have mobile things, it's not.
But for mobile things, it's the same. What's the instantaneous expectation in this area?
Yeah, I think it should be that way.
So, I mean, you can do the same thing in a museum, like how many people are in this room at any given
Yeah.
time.
The slightly other point that I was making is for applications in which the application does not specify where a transmitter needs to be, and I can actually change that. It's just temperature. I can, if it helps me, I can change the location
yeah.
of the transmitter.
Then, I mean,
You
can
could
do the
invert it.
opposite
You could
way.
have the same algorithm, the receivers are fixed and the transmitters are mobile.
Yeah.
So the sides of the graph would be flipped, but it would be basically the same. I guess what I wanted to get at with this is that, F-Embed has a different intuition than what you normally expect. So this is a circular placement of transmitters. These gray circles are transmitters, and the red triangles are receivers. And if you just kind of maybe eyeball it, you might do something like this. So I put the receivers in kind of equilateral triangle that are sort of close to the edges. But that's not the right thing. So the right intuition is actually, you want to put the receivers like right on top of as many transmitters as possible to take advantage of capture effect, right? You really want them to be as super close as possible to as many transmitters. So this is actually wrong, or not wrong, but doesn't deliver as good performance as this, where you put the receivers like right on top of those densest clusters of transmitters. Okay, and that maximizes capture effect. So the other thing you should be aware of is that it's a little bit hard to see, but the strength of the line is the probability of capturing a packet, assuming uniform transmission. And so what we've done is we've maximized the overall throughput by creating unfairness. Okay, so some of the transmitters getting screwed, like this one. Okay, so this one in this regime had an 80% chance of transmitting the packet correctly, but in this regime it only has 6% chance. Okay, so what we did was we made all these ones better by sacrificing this one. That's one way to think about it. Okay. So the overall channel utilization is maximized, okay, at the cost of fairness. So right here, this is like a more fair distribution.
But is that something we can change? Like, can we give fairness more preference?
Really, you should add
Right.
another receiver. Right, I mean, if you look at that, it's
No,
sort of obvious
right.
that there's a blank
So-
spot that is begging for another receiver.
Right, if you add another receiver, then the network becomes much more fair. So, no, that's a good point, right? You could, so we have thought about, I don't know if we have an algorithm, how do you maximize fairness as opposed to overall channel capacity?
I mean, but it's not like in the naive one, it's all that fair. I mean, look, there are some that only get like 0.2
Yeah.
in the naive one, and none of them are above 70%-ish, it looks like.
So,
Right, so it's not like the other one's all that fair, it's just that
No.
they're all sort of bad
yeah,
together.
no, the naive
No, that's
could be
more
bad,
fair,
but
because
can-
everyone's equal.
Do you want color versions of these?
This is probably fine.
No, but
The color makes it really easy to tell if it's crap versus good.
So the total, the throughput should depends on the load of the total load, right? The data rate.
The maximum.
Yeah,
This is why
if
you should
the-
use contention as the metric.
Okay.
Yeah. So if the contention probability will affect the total
Yeah.
throughput.
Yeah. Well, so if you read the paper, we actually use the contention as the but
what is the rough gain in the left and the right, between the left and the right? Like,
oh,
order.
I don't know actually. I mean, you could add up all these number of nodes times probability,
Yeah.
number of nodes times probability, but I don't know. I don't know if you guys have that data easily. If it's too hard to get there.
There is also some dark nodes. What is dark node?
Right, so the dark nodes just have a very high probability, over 90% likelihood of.
What is he asking?
Average. Okay, so the average transmitter
So,
tension was.
okay, so what this is trying to show is the number of, this is just analytic modeling. So this is the number of transmitters versus the channel utilization as we add transmitters with, or receivers with transmit only. Okay, and you can see here that, right, with one receiver, okay, we actually get above 18% because of we're actually modeling the capture effect on like Aloha. Okay? But you can see here that the efficiency does fall to, under 20%, which is in line with what you expect from Aloha. Okay, but if we start adding receivers, we can get back channel utilization, and even with 4 receivers, we're at utilization of potentially 90%. Okay. So the result, what I want to get here, and this is CSMA, just as a comparison. So the point of this slide is that you don't really need a lot of receivers, okay, to get back the channel efficiency. Okay, so here, even with 3,000 transmitters and 4 receivers, you're still getting decent channel efficiency, on the same order as CSMA.
So what is the meaning of like CSMA with max 3 CCMA?
I think that's max that's retries.
Max number of retries.
Retries.
Channels.
3 retransmission.
Yeah.
Transmission.
3 retransmissions.
So we could, instead of
So-
that graph, you could use the one with P persistent instead.
Yeah, I mean, CSMA with 3 retries is a reasonable version of CSMA. So. Yeah, you're right. So P persistent CSMA can get close to 1. You're trading latency for throughput, but. And then low power polling was, I need to reference that link somewhere. So that's like another protocol. That's more low power than CSMA. But right from the system.
It's a slotted sort of TDMA-like system.
Yeah.
There's synchronization.
Right. What I want to get right. You don't really need that many receivers to make this work.
So this is a simulation, right? This is
It's analytic modeling.
modeling. Yeah. So this 3,000 transmitters in what?
In like one, I don't know, rectangle, like unit. Where, I mean,
It's just the transmission power.
everybody's in range. I think the transmission power went from, I don't know what the dB range of the transmission power was. In that
It's a
simulation.
normalized
So-
dB.
Does
So
it
there's
go
an integral
from
and
like
some
90?
math, but there's an expectation.
Yeah.
So yeah, it assumes a uniform distribution.
Uniform distribution.
Yeah, and then you assume some, for different
dB
radio devices,
range.
right, there's a different relative distance
Relative.
you have to have. And the relative distance for that is probably the 6 dB, which is what it is for the
60
CC.
dB, okay.
So actually for a good radio, it's much less. For a good radio, it can be less than a dB.
No, but I guess for the modeling, what did you assume the max dB range was of the range of the
Right,
model?
right.
No, that doesn't matter. It's only the relative distance that matters.
Okay.
Right, because dB, right, some difference in dB corresponds to some relative distance.
Yeah,
So you assume
okay.
some, regular propagation model, 1 over,
Yeah.
R to the alpha or something. So we assumed in that, I think, an alpha of 3 and a required distance of 6 dB, which corresponds to something like the closer one has to be 2/3 the distance of the further one, or something like that.
No, but how was I guess with 3,000 nodes, they're all like together.
Okay,
Then you wouldn't get any capture
there's an
effect
integral.
versus the spread. Yeah.
There's an integral, and it's in my thesis. And I mean, you could go through the integral, but basically, that
It's something like how spread out they are. So.
10 to the negative delta over 10 alpha, right, gives you some relative constant between the two, relative distance that the two have to be, right, where delta is the number of dB difference. So it's 10 to the negative 6 over 10 alpha. So if alpha was 3, that would be 10 to the negative 6 over 30, which is 10 to the minus 1. So there's some relative distance there.
I guess the question is, for any 2 nodes, what's the likelihood of them being captured or something?
Then it's that number then over 2, if you assume a.
So if all the nodes are in the same Kyber system.
Yeah, it's just a uniform distribution on a field of any.
It's a uniform distribution of the field, but right, unless you know this probability of capture or not, it's going to.
So I mean, it does. So for instance, if you assume that you have better receivers, or actually if propagation gets worse, TO does better.
Yeah.
And if
the receiver difference gets better,
yeah, if your
or you can discriminate less dB.
Sensitivity gets better, then it also gets better. So it's inversely proportional to channel to signal propagation and directly proportional to receiver sensitivity.
But I guess for this model, you don't know exactly what it is.
No, it was 6 dB
Right.
with alpha equals 3.
Okay.
And you assume receivers at optimal positions.
No, that's purely probabilistic. Like I said, there's an integral. You integrate over a uniform space, assuming some distance, and you get some probability.
The receivers in 1, 2, 3, or 4 receivers.
Looking at the receivers independently. Assuming each one is independent. So that one, that's a purely analytic.
No capture effect.
Right. It's just analytic modeling.
And this receiver, you use this embed to place the receiver?
No, so this is purely analytic. So for that one, to determine the probability of packet loss, what you do
And
is you
so
say this
assuming you place the receiver at what is the position, or you're assuming at the
no, it's purely analytic. There's no transmitter placement, there's no receiver placement, it's all analytic.
Right, so I think getting at his question is what, if you have multiple receivers, how does that scale in your model? Is it the probability, just based on the probability of capture?
So you're just assuming each one, this one just assumes that each one is
Independent, right.
Right, so if you had an infinite,
Okay.
if you assume an infinite number of transmitters, then they're independent. If you only have like 2 or 3 transmitters, then obviously at some point, one transmitter is right next to one receiver.
You just model
There's
this
not
coin
independent
flipping
between
of
them.
receiving the packet, and then if these are independent, it's like additive.
Yeah. Add them together.
Yeah.
So
It's just additive probability.
independent and receiver, it's the same thing.
Right, you're assuming independent, so it's additive probability.
And we've done experiments now, and it's about right. Doesn't match perfectly with the real world, and that's because the real world has some, has physical boundary constraints. Right? So this is sort of assuming a kind of an infinite field of uniformly distributed.
The real world,
So
probably.
here's real world.
Better.
Here's Rob with the real world. So okay, here's 500 transmitters. Okay, I don't know if people have seen Rob and Ben. Okay. So each of these black triangles was a bundle of the TO nodes, and then each of these was a message-in-message receiver, which is with a pair of cheap receivers. And then we wanted to see if the actual data matched the analytic modeling, and the answer is yes. It's reasonably close. So the blue line is a naive theoretical model, and this shows this duality. If you're transmitting once a second, the channel load on the x-axis versus the throughput per packet time on the y-axis. Okay, so you can think of throughput per packet time as, right, if it was 1, then every packet transmission time we're getting 1 packet. Okay, so this is like 20% channel utilization. And then this is sort of transmitting at once a second, what's the number of transmitters, and then A is the offered packets per second per packet time. So we see here the naive theoretical model, and then the red line is using F-Embed, and the green line is using equilateral triangle. So you see if the field's roughly random, then F-Embed is about what it's also an equilateral triangle, and it's not the same performance. The other thing is that the analytic modeling versus the measurement is not that far off, actually. So it's well within 80% of, or even 90% of the naive theoretical model. So the point of this slide is that our models are roughly correct for this transfer with capture effect. Just a couple slides on applications, sort of running a little bit over. So this is the OWL platform. So then, let's say we had this great transmit only layer. Can we actually take advantage of it to build applications? And yes, because we built some. And we have these, we've moved the aggregation and data analysis layers out of the sensor network. Okay, so getting at, less is better. Okay, so we made the sensing layer less, and we put the aggregation and analysis layers outside in regular computers, you can write regular applications. So a couple of applications we have, very simple things like leak detection. So if you sense standing water, send an email like on your water heater. Office space assignment. So Rob's actually trying to deploy this application right now. Right. So how heavily or lightly loaded are various student offices, so we can do office assignment. Fresh coffee was running for a while, though I guess that's fallen off of that. One student wrote a chair stolen application from last summer. Okay, so the idea here is it's actually much weaker than localization. So it's just, is the chair in close enough proximity to the cubicle that it's okay, and if it moves away, then you want to get notified because it's somebody's stealing your chair. And then another student once wrote a loaner bicycle inventory control application. This was 2 summers ago, I guess. So it is, if bicycles move in and out of this room, then how many bikes are left? So you just want to know, like, is there a bike in the room? If there's no bike in the room, I don't want to go hike over and then not find a bike. So this is just counting the number of bicycles.
So none of them are energy applications?
Well, I mean, the idea here is if I need my sensor to be deployed in some space that's not connected to power or on something that's mobile, then I need low energy. Because I don't want to change the batteries all the time. Like for leak detection, I don't want to run down every 3 months to change the batteries for this application. It's too much hassle. For office space assignments, I put them on the doors, and then I don't want to have to keep changing the batteries all the time. Fresh coffee, you could argue, has access to wire power. Chair stolen, again, mobile object, and loaner bicycles are mobile objects. So.
Right, I mean, the comment was, it's sort of hard now to sort of turn things on or off, depending on residence and so on, to save energy. So, I mean, has that been sort of intentionally left out? No one likes the energy applications?
Well, yes, in the sense that the higher layers are much more complicated, and the infrastructure you need to actually. So, yes, in 2 senses. One, it's more complicated, and 2, that requires actuation.
Right.
Okay, so.
I mean, the actuation loop could be a separate.
Right. So in the OWL platform, we made a conscious decision to actually not do actuation and leave that as a separate stack. Okay. So we haven't gotten to the other stack yet. So OWL is mostly about notification and not about actuation. Because actuation introduces all kinds of security issues that are much harder to solve than just presenting data. So presenting data has some security issues, but actuation has a lot of security issues.
Medical and automotive are the same way.
Yeah.
Like, there are a lot of things you could do in either of those fields, but you've got to get into the system.
Yeah. I mean,
Not easy.
the cost for a screw up in a sensing application is much less. Like if somebody accidentally breaks in my read my data, yeah, it's less bad. But if they can actually control stuff, that could have much worse.
But using the old the bi-direction sensor, so you're able to switch off and on the left, right?
But that's a very small number of sensors compared to the number of ones that you want to have sensing.
Yeah,
Right, so
I
you may as well
mean,
have
if you want to demonstrate some energy control demo.
No, it's not necessarily just control. To be able to monitor energy usage.
Right, so that we could do, but we didn't.
Yeah, I mean, we have energy monitoring. We had one connected to that. I think you can see there's a pit connected over there on that totally unsafe power box over there. You see there's a pit connected that does energy monitoring. Right,
So we have energy monitoring sensors, but one of the things that we realized going through this research, and this is a problem the sensor network community's had for a long time, which is, unless you're changing some human behavior somewhere,
It just makes you more anxiety.
It just gives you more anxiety. It's not worth it. Like it's not a real application. Like it doesn't really have value unless. So for energy monitoring, right, you're changing the behavior of the building. Okay, so it's changing the behavior of something.
Right.
But most applications, you actually want to change the behavior of like the people, right? So for the vineyard application, it's a good example, right? They want to change when they can actually go out and pick the grapes. Okay, so it's like people changing behavior. Even for energy, right, you might want to change not just the behavior of the building, but if you want to have people change where they go, potentially, to save energy. Like if they could use less of the building, then you can save energy.
For some,
think about how do you impact human behavior with this sense data? That's really where our thinking has been. So the actuation side. Yeah. Any question?
Yeah, I mean, some monitoring will like help people to change their behavior, like definitely, right? It's like instead of anxiety, like for example, if you have you monitor your TV on off, and then you realize you watch too much TV for a month or something.
No, right. I mean, health applications are in that mode where
That's right.
they try to get you to change your behavior based on sensitivity.
Right.
Yeah. No. I mean, we haven't looked at health applications. That's another thing. So, just some conclusion. So, to answer those questions, channel utilization we can actually achieve very well. The receiver network, sort of rule of thumb is that you need 1 to 5% of the number of transmitters, depending on the receiver placement and the load. But for realistic loads, it's about maybe max out 5%. So it's not really that many receivers. The receiver is actually pretty simple. So messaging receiver is pretty simple. So one of the minuses is that the receivers need continuous power in order to store it, or so far. So if you can get your receivers continuous power, then this is a great idea. If not, then maybe not. And then the backhaul bandwidth is sort of like 3 to 4x the sensor input bandwidth. So this wasn't like you need 10x or 1000x. So it is more, but it's not hugely more. Manageability, we're working on something called transmit mostly. So, you know, like every 1,000 or 10,000 packets, you can send a command, and the receiver figures out everything about when to send it. So that's where our mind is with manageability. And security, we have little to no ideas about security. So it's still very open.